Memoria Scholae is a research assistant engineered to remember, reason, and accelerate discovery. At its core, we combine two complementary primitives: a persistent vector-backed memory layer and a graph-native reasoning engine. The memory layer, machine, stores episodic, semantic, and procedural records with lightweight metadata and embeddings. It exposes fast HTTP endpoints for store and search, so a researcher's session becomes recallable context. Session transcripts, paper notes, experimental observations, all retrievable with sub-100 millisecond recall. On the other side, Neo4j holds structured scientific knowledge as nodes and type relationships. We use cipher-powered multi-hop queries for bridge discovery, shortest path and constrained variable length patterns, combined with novelty scoring that weights degree centrality and rarity to surface unexpected 2 to 4 degrees connections between concepts. Technically, Memoria Scholae routes natural language queries through a LangGraph orchestration layer. LangGraph dispatches tasks to specialized agents: the Pi router, literature ingesters, synthesizers, critics, and hypothesis validators. Agents read and write to machine via its REST API and to Neo4j via secure Bolt plus TLS connections, Neo4j plus s://URIs, or fallbacks in dev. We enforce schema constraints and indexes on Neo4j for concept.name and paper.doi, enabling millisecond cipher lookups. Multi-hop reasoning leverages APOC where available for advanced path scoring and temporal filtering. We instrument everything: machine query latency, Neo4j cipher latency, agent task durations, and end-to-end P95 targets. Safety is baked in with confidence thresholds in HITL gating. Outputs under 85% confidence route to a human reviewer, with full SHA-256 audit traces stored in the audit log. This is not hypothetical. The platform demonstrates persistent agent memory combined with graph-native reasoning. That combination is what enables compound learning. The system doesn't just answer once, it updates its knowledge, reuses past experiments, and suggests novel hypotheses by finding bridges. Neo4j exposes through graph traversal and machine contextualizes with session history. Open Research App. This page is the primary user workflow. Enter a natural language research query, attach PDFs like a protein folding example, or paste experiment logs. When you submit, the Pi agent first performs semantic routing by querying machine for related episodic and semantic records. That recall provides immediate contextual evidence, past notes that mention similar methods, prior parameter sweeps, and related citations. Next, the literature and synthesizer agents extract entities and push structured nodes into Neo4j, papers, methods, metrics, and conceptual links. The Research App UI displays both a timeline of recalled memories and the Neo4j-backed graph view so you can inspect provenance for every assertion. A 6-agent orchestra with persistent memory and graph reasoning, how it works and what problems it solves, forgotten context, blind spot discovery across disciplines, and reproducibility gaps. The video highlights a live query: connect transformers to protein folding. machine recalls 2 prior sessions about attention maps. Neo4j returns a 3-hop bridge, self-attention geometric reasoning protein contacts, and the synthesizer agent produces a hypothesis with provenance, experiment notes, supporting papers, and a projected metric improvement. All steps are time-stamped and auditable. Agent orchestra expands on the runtime. Each agent is a bounded task. PI handles semantic routing, literature ingests PDFs and populates Neo4j. Critic runs automated checks and cross-validates claims against prior experiments.